Okay, let's unpack this. Imagine this. You train base LLMs on math problems, right?
Right. You pour in all this data.
And what happens? They fumble through something like AM 2024, scoring a dismal 26.7%.
Yeah. It's underwhelming
You
sometimes.
throw your hands up,
Yeah.
then you look to cognitive psychology.
A bit of a left turn, maybe.
And you see reasoning is modular, sequential operations. So you build 4 tools: understand question, recall related, examine answer, backtrack.
Inspired by how we think, essentially.
You let the LLM call them when it wants. No new training, just prompting.
Just guiding it.
And GPT 4.1 jumps to 43.3% on AME 2024, nearly matches O1 preview.
That's a huge leap.
You test on Quen 2.532B, baseline flounders at 17.2% on A.
Yeah. Really struggling?
With tools, 32.1%, boom.
Doubled. Almost.
You try cognitive prompting, the older idea. It's rigid, forces steps in order.
Yeah. Very structured. Maybe too structured.
Your tools. Flexible, let the model choose. Llama 3.3 70UB with tools hits 80% on small benchmark.
80%.
Executive prompting, only 66%.
The flexibility clearly helps.
You check if RL, reinforcement learning, is needed. Note tools work on base models.
Which is fascinating.
They just uncover latent reasoning. Someone says it's just math.
The classic dismissal.
You point to the mechanism. Modularity reduces interference. Flexibility lets reasoning flow.
It's how it works that matters.
You test across benchmarks, Math 500, AMC, some mall benchmark, all climb.
Consistent improvement.
You realize you didn't train a math solver. You built a way to unlock reasoning hidden in the LLM's weights.
That inherent capability.
They say, but it's just 4 tools. You show the chain, understand, frames the problem, pulls similar solutions, examine, catches mistakes, backtrack, fixes paths.
Together they form a sort of reasoning engine.
They say, but closed models are better. Your open models with tools close the gap.
Democratizing it, in a way.
They go quiet. You realize you didn't make a better LLM.
Not in the traditional training sense.
You made a bridge between how humans reason and how machines can, if you let them use the right tools.
That's the core idea, really.
So that's the journey, and today we're diving deep into this fascinating paper that promises exactly that, bridging human and machine reasoning with these internal cognitive tools.
It's an incredibly intriguing premise, definitely. This deep dive is truly about uncovering those latent reasoning capabilities in large language models.
Right.
It kind of moves beyond just brute forcing them with more data or, complex traditional training.
Yeah.
And really focuses on that aha moment of allowing models to think more strategically, maybe more like us, using these structured internal operations.
Okay, so to really get why this is such a big deal, maybe we should rewind a bit to what you called the great LLM reasoning mystery.
Exactly. Let's set the scene.
When models like OpenAI's O1 preview first showed up, wow, they had these incredible leaps in complex tasks, especially reasoning. Huge excitement.
Massive excitement and intense speculation.
And the big question was, how? How did they suddenly get so good? What was the secret sauce?
Yeah, precisely. And the initial theory, the one that really took hold, was reinforcement learning, specifically RLHF, from human feedback.
Right, that was the buzzword.
The idea was that RL was directly infusing powerful, new reasoning capabilities into the base models.
No, RL was teaching them to reason better.
That was the thought. And work like DeepSeek R1 seemed to back this up. They showed that, combining supervised fine-tuning with RL optimization on these carefully curated reasoning traces.
Reasoning traces, like step-by-step thinking.
Exactly. Step-by-step examples of good reasoning coupled with verifiable rewards. It looked like RL was the key ingredient to get those impressive results. Seemed settled.
Seemed settled, but then plot twist.
Always a plot twist in AI research, isn't there?
Seems like it. So newer analyses came out. You mentioned Liu et al. And Yu et al., both pretty recent, 2025.
That's right. And they threw a pretty big wrench in that whole RL infuses reasoning theory.
What did they find?
Well, they found something kind of surprising. The base models, the ones before all that fancy RL fine-tuning, they already had strong, latent reasoning abilities. Hidden depths, you could say.
Latent, so they could already do it, but weren't showing it.
Pretty much. They even showed patterns of aha moment, self-reflection, like suddenly correcting themselves or finding a key insight.
Wow. And we thought only the super-tuned models did that.
Exactly. That was supposed to be the hallmark of the advanced RL-tuned ones.
Yeah.
So this finding really changed the picture.
So what does RL do then, according to this newer analysis?
Well, according to Liu and Yu, RL doesn't necessarily create new reasoning skills. It acts more like a powerful filter, maybe.
To filter? How so?
It biases the model's output. It pushes it towards generating those desirable high-reward reasoning traces, the ones that look like good reasoning.
Ah, okay. So it's like it encourages the model to use the good reasoning pathways it already has.
Precisely. It's effectively uncovering or highlighting capabilities that were already present, just lying dormant in the LM's weights.
Okay, that makes sense. But it raises a huge question then.
Which is,
if RL isn't strictly necessary to create reasoning, but just to surface it, what else can we do? How else can we unlock that latent power?
and that, right there, is the perfect bridge to the next big idea in this paper.
Which is looking at us, looking at humans.
Exactly. If we want LLMs to reason better, why not look at the best reasoners we know?
Yeah.
Us, the human brain.
Makes sense. So cognitive psychology comes back into play.
Right. And established cognitive architectures, things like ACTR from J.R. Anderson, become the inspiration.
ACTR, I've heard of that. It models human cognition, right?
Yeah, a classic framework. And the core insight, the really useful bit here, is that human reasoning isn't just one big black box. It's modular.
Modular, meaning different parts do different things.
Kind of. It involves sequential, coordinated operations. Like first you understand the goal, then you break down the problem, then you recall relevant stuff, specific steps.
Okay, I see where this is going. So people try to apply this to LLMs.
We did. Kramer and Bauman, back in 2024, explored something called cognitive prompting.
Cognitive prompting, what was that like?
It was basically an early attempt to translate these human-inspired ideas. It involved guiding the LLM through stages, like goal clarification, problem decomposition.
The steps you just mentioned.
Exactly. But typically using a single big structured prompt. A monolithic prompt, you might say.
Yeah. One giant prompt telling it how to think, step by step.
Pretty much. And it's a step forward, definitely promising, making LLMs think more systematically.
Okay, sounds good on the surface. But you hinted it wasn't the final answer. What was the downside? Where did it fall short?
That's the key point. While it was innovative, cognitive prompting had a major limitation.
Yeah.
It was, well, rigid.
Rigid, like too inflexible.
Yeah. It forced the LLM through this predetermined order of operations, all crammed into that one massive prompt.
And that's bad because
Because it risks interference. Different cognitive operations kind of stepping on each other's toes within that single prompt context.
interference, like trying to recall information while also trying to verify an answer might mess things up.
Exactly. It just lacked the true modularity and, crucially, the flexibility that human thinking often has when we tackle complex problems. We switch strategies, we backtrack, we focus on one aspect then another.
Okay, so the rigidity and lack of modularity were the hurdles.
Right. Which leads us directly to the core innovation of the paper we're really digging into today.
Which is cognitive tools.
Bingo. Cognitive tools.
And you got to stress, these aren't the usual tools people talk about with LLMs, right? Not external APIs or calculators.
That's a crucial distinction, yeah. Many agent frameworks use external tools, like calling a calculator or a search engine. These cognitive tools are different.
How so?
They are reasoning operations encapsulated within the LM itself. They live inside the model, so to speak.
Okay, internal tools. And the key difference from cognitive prompting is
Modularity. Each tool is a discrete, self-contained function. Think of it like a specialized mini-program within the LLM, each with its own specific prompt template.
so instead of one giant prompt, you have several smaller, focused prompts for different tasks.
Precisely. Like having specialized mental functions ready to go internally.
And that's the game changer, you said. Because unlike rigid cognitive prompting,
Right. Cognitive tools allow the LLM to actually decide which specific tool to call and when to call it. It's not forced into a sequence.
it gets to choose. It's like, okay, instead of giving someone a detailed instruction manual for building something, you give them a toolbox.
That's a great analogy. A toolbox.
Yeah.
And the LLM can pick the right wrench or the right screwdriver for the specific part of the problem it's facing right then.
Instead of being forced to use a screwdriver for everything, like in the monolithic prompt.
Exactly. Much more flexible, much more adaptive.
But wait, if you give the LLM more choice, doesn't that open up the possibility of it making the wrong choice, picking the wrong tool, or using it badly? Is there a risk there?
That's a totally fair question. And that's where the overarching cognitive tools prompt comes into play.
Ah, another prompt.
Yeah, but this one is more like a system prompt. It acts as the LLM's guiding rules. It tells it, call a tool when you think it's needed. Here's how to format the call. And crucially, never hallucinate results from a tool. Wait for the actual output.
Okay, so there are guardrails. But how does the actual process work? When it decides to use a tool, what happens?
It's actually quite elegant, and it helps manage that risk. So the LLM is generating its reasoning step by step. It decides, okay, I need to double check my calculation. It signals it wants to use the examine answer tool.
Right.
Then its main generation process pauses. And here's the cool part. The same LLM instance is used, but in a kind of sandboxed context.
Sandboxed, like separate.
Yeah, temporarily separate.
Yeah.
It gets fed this specific prompt tailored just for that tool, the examine answer prompt, in this case, along with the relevant part of its current reasoning.
Okay.
The LLM then executes that tool's specific function, checking the reasoning, performing the calculation, whatever it is. It produces a structured output.
Structured output, not just more text.
Often, yeah. Like a confirmation or a corrected value or a list of examples. That structured output is then fed back into the main reasoning loop where the LLM was paused.
I see. So it pauses, runs the tool internally, gets a clear result, and then continues its main thought process with that new information.
Exactly. It's this iterative process. Pause, call tool, get result, integrate, continue reasoning. And because each step is tied to a specific tool call and its output, it makes the whole thing surprisingly transparent and easier to trace. You can see the thought process.
Okay, that's much clearer. Very cool. So let's meet these tools. The paper talks about 4 main ones, right? Inspired by human cognition.
4 core ones, plus an important helper.
All right. First up, question. What's the inspiration here?
This one's inspired by goal management in human cognition. Think about how we first tackle a complex problem.
We try to figure out what's actually being asked, right? Break it down.
Precisely. So this tool helps the LLM do that. Break down the problem, identify the core concepts, pull out the relevant info, maybe even highlight useful theorems or formulas it knows. It's like the initial brainstorming or problem framing stage.
Got it.
Tool number 2.
Recall related. This is inspired by analogical reasoning. You know how we often solve new problems by thinking of similar ones we've solved before?
Like saying, this math problem looks kind of like that one I did last week.
Exactly. So this tool prompts the LLM to access its own vast knowledge base and pull up relevant solved examples of similar problems. It gives the model a template or a successful path to potentially follow.
Okay, that makes sense.
Number 3.
Examine answer. This one is huge. It's inspired by self-reflection, self-correction. Think of techniques like reflection that came out a bit earlier.
The LLM checking its own work.
Literally. It prompts the LLM to critically review its current line of reasoning. Look for flaws, wrong assumptions, calculation errors, check if it's following the rules or constraints.
That's fantastic. We could all use a button for that sometimes.
Tell me about it. It's about catching mistakes before they derail the whole solution.
All right, and the 4th core cognitive tool.
Backtracking. This is inspired by search algorithms like Monte Carlo tree search, stuff used in game-playing AI.
Backtracking, like hitting a dead end and going back.
Exactly. It allows the LLM, if it realizes it's gone down a wrong path or made a mistake it can't easily fix, to identify that incorrect step, revert back to a previously valid point in its reasoning.
Like hitting undo.
A mental undo, yeah. And then explore a different, hopefully more promising, reasoning path from that valid point. It stops it from just getting stuck.
Okay, understand, recall, examine, backtrack. Those are the 4 core ones. You mentioned a helper tool, too.
Yes, the crucial use code tool. Now, this isn't strictly cognitive in the human sense, perhaps.
Right, we don't run Python in our heads, usually.
Hopefully not. But it acts as another modular function the LLM can call. It allows the LLM to generate and execute Python code, usually for computation.
Like grabbing a calculator.
Exactly. If it needs to do complex arithmetic or run a specific algorithm, it can generate the code, execute it, presumably in a safe environment, and get the result back, just like with the other tools.
Very neat. So it's got these internal cognitive tools and this computational helper tool, all guided by that overarching system prompt.
That's the framework.
Okay, let's make this concrete. The paper has this great example, right? The GCD one.
The greatest common divisor example, yeah. It really shows the difference.
So the task is finding the GCD of 3 numbers, 3339, 2961, and 1491. What happens with the standard LLM, like the baseline Llama 3.18b they used?
Well, the baseline model, it fumbles. It knows it should probably use the Euclidean algorithm, which is the right method.
Okay, so it has the basic knowledge.
It does, but it makes a mistake somewhere in applying it, a subtle error. And it ends up concluding the GCD is 3.
Which is wrong. The actual answer is
21.
Okay, so baseline gets it wrong despite knowing the right algorithm. Now, give that same llama model the cognitive tools. What happens?
It's a totally different story. First, it calls understand question.
Okay, frames the problem.
Right. It breaks it down. Find GCD, number theory, suggests using the Euclidean algorithm. Sets the stage.
Then what? Does it try the math itself?
Nope. It decides it needs computational help for accuracy, so it calls use code.
Ah, smart move.
It generates a little Python function, GCD3 numbers, that correctly uses the math.gcd function iteratively.
And the code runs.
The code execution returns the result. The GCD is 21.
Correct. But does it just stop there and give the answer?
This is the crucial part. No, it doesn't. It then calls examine answer.
It checks the code's work.
Exactly. It self-verifies.
Yeah.
It analyzes the Python code it just generated, checks the logic, confirms the result. 21 seems plausible for the input numbers. It even proposes its own test cases to validate the code further.
Wow, it suggests tests like, what if one number is 0? Or what about negatives?
Yeah, stuff like that. It really rigorously checks its own work and the tool's output.
And only after that successful self-check.
Only then does it confidently output the final correct answer.
21.
That's a night and day difference. Structured, verifiable, self-correcting reasoning versus, well, fumbling.
Precisely. It really highlights the power of this structured tool-using approach.
Okay, compelling anecdote. But does it scale? What do the benchmark numbers say? You mentioned they used tough math tests.
They did. AME 2024, Math 500, AMC, small benchmark. Chosen specifically because math gives you clear right-wrong answers. Easy to quantify the improvement in reasoning.
Makes sense. So what did they find? Did the tools help consistently?
Absolutely. The numbers really back it up strongly. First, they looked at individual tools.
Just adding one tool at a time.
Yeah, or looking at their impact. And each tool provided a noticeable boost. For instance, just adding the backtracking tool alone gave Llama 3.3-70B and struck a huge plus 26.7% jump on small benchmark.
Wow, just from being able to backtrack.
It's significant, right?
Right.
Then they compared the full cognitive tool setup against the older cognitive prompting idea.
The flexible toolbox versus the rigid instruction manual. Exactly. And the modular cognitive tools consistently outperform the rigid cognitive prompting. Across different models, too.
Like what kind of gains?
Well, the performance increases ranged from a solid plus 4.2% on a smaller model, like Qwen 2.57b Instruct, up to a massive plus 27.2% gain on the big Llama 3.370b model compared to its baseline performance.
So across the board, the modular flexible tool approach was just better.
Clearly validating the benefits of that modularity and flexibility we talked about.
Okay, but then comes the comparison you called the mic drop moment, the GPT 4.1 result.
Yeah, this one's really eye-opening. So they took GPT 4.1, a very powerful but closed proprietary model.
Right.
On the AME 2024 benchmark, its baseline score was 26.7%, the same score the other model got before tools.
Okay, and then they equipped it with these cognitive tools. No retraining, just the prompting framework.
Exactly. No retraining of GPT 4.1 itself, just gave the tools via prompting, and its score soared to 43.3%.
From 26.7% to 43.3%, just with the tools.
Just with the tools. And here's the kicker, that 43.3% nearly matches OpenAI's own O1 preview model, which scored 44.6%.
Whoa. And O1 preview is thought to be heavily RL tuned for reasoning, right?
That's the general understanding, yes. Known for its powerful reasoning, likely achieved through intensive RL.
So a base model, GPT 4.1, without extra RL tuning, but with these cognitive tools, performs almost as well on this tough reasoning path as a model specifically tuned with RL for reasoning.
That's what the results strongly suggest.
And that's the critical point, isn't it? This huge leak happened without any additional training of GPT 4.1.
Precisely. It wasn't about more data, more parameters, more fine-tuning in the traditional sense. It was about unlocking existing potential through a better workflow.
Which loops back to that earlier idea.
Right. It strongly supports the hypothesis that these advanced reasoning capabilities might be largely inherent or latent within powerful pre-trained models.
Already baked in from the pre-training phase.
Seems likely. And these tools provide a structured way to effectively surface and utilize that latent potential. It suggests RL isn't the only way to get great reasoning, and maybe its primary role is more about harnessing or biasing towards existing capabilities rather than creating totally new ones.
Okay, this is huge. So let's zoom out. What does this all mean for, for you listening? This is clearly more than just getting LLMs to do math homework better.
Oh, absolutely. The implications are much broader.
Like what? What are the big takeaways here?
Well, first, as we've been saying, it really fuels the debate about where reasoning in LLMs actually comes from. It gives strong evidence for the latent ability view that pre-training does a lot of the heavy lifting, and methods like these tools can unlock it. It offers an alternative, or at least a powerful complement, to very expensive, resource-intensive RL fine-tuning pipelines.
Which could be massive for researchers or companies without Google-level resources.
Oh, exactly, which ties into the second point,
Oh.
transparency and explainability.
Ah, the black box problem. How does this help?
By structuring the reasoning into these discrete, interpretable steps tied to specific tool calls, you can actually follow the thought process much better.
Like we saw in the GCD example, you see it call understand, then use code, then examine.
Precisely. You get a trace. This is crucial for applications where you need to understand why the AI made a certain decision. Think healthcare, finance, education, legal reasoning.
Anywhere trust and accountability matter, which is pretty much everywhere we want to use AI seriously.
You got it. And third, building on the resource point democratization.
How so?
Because this cognitive tools approach works well even on base models, including open source ones, it potentially democratizes access to advanced reasoning capabilities. You might not need access to a giant proprietary RL fine-tuned model to get sophisticated reasoning for your application.
You could potentially get close using an open model with this framework layered on top.
That's the promise. It levels the playing field somewhat. And maybe the most profound implication is that it genuinely creates a bridge, a conceptual bridge between how we as humans think using modular operations, different strategies, self-correction, and how machines can reason if we give them the right kind of internal scaffolding. It makes AI reasoning feel a little less alien, perhaps.
Making it think more like us by giving it tools that mirror our own cognitive processes. That's pretty cool. Now, we should be fair. No research is perfect. Are there limitations here?
Of course, and the authors acknowledge them. Right now, these cognitive tools are manually defined. Someone had to design, understand question, recall related, etc.
So they didn't emerge automatically.
Not yet. Also, the main evaluation focus was heavily on mathematical reasoning. While that's great for clear benchmarks, we need to see how well this transfers to other complex reasoning domains like creative writing, scientific hypothesis generation, legal arguments.
Does it work beyond math? Still an open question partly.
And there might be some prompt engineering needed to get the best performance out of these tools on different model families. It might not be perfectly plug and play for every single LLM out there just yet.
Fair enough. What about future work? Where does this go next?
Well, the obvious next step is trying to automate the discovery of useful cognitive operations or tools rather than handcrafting them.
Could the AI learn its own best tools?
That's the dream. Also, exploring deeper integrations with RL, maybe using RL to tune how the model selects and uses these cognitive tools, combining the best of both worlds.
Interesting. Using RL to optimize the tool use, not just the final output.
Potentially. And of course, applying and testing this modular, tool-based reasoning framework across much broader domains beyond mathematics, seeing if it holds up for, say, common sense reasoning or planning tasks.
Lots of exciting avenues to explore. So, wrapping this up, the core insight from this deep dive seems to be we didn't necessarily build a fundamentally smarter LLM in the traditional training sense. Instead, this research found a way to unlock the powerful reasoning capabilities that seem to be already hiding within the weights of existing models.
By giving them the right framework, the right tools to structure their thinking.
It's like we found this incredibly powerful engine, the pre-trained LLM, but it needed a better operating system, these cognitive tools, to really perform at its peak potential for complex reasoning.
This is a really good way to put it. An intuitive interface for the model's own latent abilities.
Which leaves us, and you listening, with a pretty provocative final thought, doesn't it?
I think so. If just equipping an existing LLM with a handful of these modular, human-inspired cognitive tools can unlock such dramatic improvements in its innate reasoning, what other hidden, perhaps even more human-like capabilities might be lying dormant inside these complex neural networks? What other potentials are just waiting there, waiting for us to find the right prompt, the right structure, the right tool to awaken them?